Okay. Okay. So we'll discuss about energy distribution. Is there any other thing you want us to discuss so that if I just write a couple of things down? And can you see my screen?
Yes, sir.
Okay. So one of the assumptions in Druth's theory was that the energy was distributed evenly among all the electrons, so that the average energy, so he treated the electrons as an electron gas. Okay. So the average energy is just the average kinetic. Okay. So the average energy is just average kinetic energy. I mean, if you do it classically, this is exactly 3/2 kBT. Okay. For each electron. So if there are n of them, then the total energy of the system U will be n times average energy, which is 3/2 nkb. Okay. So you take C derivative. Yeah, so you take CV, which is the derivative of U at constant V. And you take the derivative, you get exactly 3/2 nkb. Okay. So at high temperatures, people already know the value of CV. Okay. At high temperatures, okay, CV is 3, the number of ions, that's KB. So people already knew this. Okay. So this is at high temperature. This is the DeLong-Petit rule. Okay. Or if you like, we can do CV over number of ions. Is 3 kV. Okay. Okay. So people already knew that all you have, that CV is proportional to number of ions. So what about the CV from the electrons? So this N is the number of electrons. Okay. So why don't you have like CV is CV from the ions plus CV from the electrons. Okay. The one from the electrons, Drude was saying that it was 3/2 number of electrons, that's KB. The one from the ions we already know is just 3 nkb. Okay. So we should get 3. So you should get 3 number of ions. Sorry, this number of ions. Number of ions. And then half n/2. This is the number of electrons, KB. Okay. But experimentally, we don't see this. Okay. When people do the experiment, they just get CV is this. So CV, what Drude is predicting was 3 number of ions plus n/2 kb. Okay. CV experiment at high temperature is like just 3 number of ions kb. Okay. So where's the heat capacity due to the electrons? It seems to be missing. Okay. So yeah, so it doesn't come into play into this in this expression. This is why when You calculate kappa, which is the thermal conductivity, CV, tau. There's some other thing which I don't remember. Okay. So it's proportional to CV and tau. Okay. So when you calculate it and you try to find kappa over sigma t, okay, you get wrong value. So Jude gives wrong value. Okay. For metals. Okay. Yes, Jude still got that is constant, wrong constant value. But the value he got was wrong, but he still got that kappa over sigma t was constant. He was the first one, as far as we know, who was able to show that kappa over sigma t was constant. So we give him credit, a lot of credit for that. Okay. Like materials that have a high thermal conductivity will also have a high electrical conductivity. And in particular, when you divide kappa over sigma and the absolute temperature, you get something that's a constant. So this problem actually originated from the fact that for experiments, the heat capacity depends on the number of ions. The contribution to the number of electrons is not there. Okay. Okay. So where is the energy due to the electrons? Okay. So we're going to see actually that when you give energy to a system, the electrons don't take the same amount of energy. Even on average, they don't take the same amount of energy. It's only the electrons near the top that take the energy. To do that, we have to develop a few tools. Okay. Okay, the first tool we'll develop is that the wave function for the electrons. Let's say in this case, let's think about two electrons. Okay, electron 1 is in state N1, electron 2 is in state N2. Okay. It turns out that the wave function for the electrons, because they're fermions, they satisfy this principle that if you interchange two electrons, if you interchange the states of the two electrons, okay, the system changes sign, okay, or if you interchange the position of the two electrons, it changes sign, okay. So this is the origin of the Fermi exclusion principle. So you see that if you try to put the two electrons, electron 1 and electron 2 in the same state, you get 0. So psi n, I try to put them in the same state. Electron 1 and electron 2, according to this expression, this should give you minus psi n. Okay, because n1 is n, n2 is n, so I put them in the same state. And okay, I have this. So this tells you clearly that psi n is 0. Okay, so that means two fermions cannot be in the same state. In this case, electrons cannot be in the same state. Okay. This is not true for bosons, because for bosons, when you interchange any two particles, the sign does not change. So there's no problem. Let me put that there. Okay. For bosons, okay. Psi N1, yeah, N2. Yes, go ahead.
Okay.
Yeah, I'm listening, Thomas. Okay, so this problem we have with fermions does not come in the case of the bosons. Many bosons can be in the same state, but for fermions, only one of them can be in a state. Okay, you can have or 0 of them in a state. You can't have more than one in a particular state. Okay, so For bosons, there's no problem. Many of them can be in the same state. But for fermions, they cannot all be in the same state. Okay. So if you put, so for electrons, if you put an electron in state K1 and spin up, okay. So I'll put an electron in this state, okay. The other electron that I put, okay. So this is the first one. The other electron that I put, I cannot put it in state K1 and spin up also. I have to put it in another state, okay. In another K state, so K1 not equal to K. Sorry, not equal to K2, or K2 not equal to K1. I have to put it in another state if I want it to spin up, okay. Or, so the second one can be there, or I can still put it in the same K state, okay. But I can't make it spin up, it has to spin down. So no two electrons can be in the same state. If one is, so by state now, so N now will be K1 and the spin. Sorry, will be K and the spin. Actually, for the spin, we use alpha or beta. No, for the spin, sorry, we use sigma. Okay. So sigma can be spin up or spin down. Or some books, we say sigma can be alpha, which is spin up, or beta, which is spin down. Okay. So instead of N here, we had N1, N2. Okay. N1 will be K1, sigma 1, and then N2 will be K2, sigma 2. Okay. Yeah. There are other things that will happen, but let's stay with this for now. Okay. Because later we saw that each band can also have an index. Okay, so we can have a band index also. But let's stay with this for now. Okay. So what does this mean for us? Okay. During one of the classes, we saw that okay, we applied the bond von Karman boundary condition. Okay, period boundary condition. Let's just call it BC. Okay. What does that mean? That means that when you have the system like this, okay. Okay, let's say this is atom 0, and then there's atom 1, there's atom 2, on, atom 3, on like that. Here will be atom n minus 2, and this will be atom n minus 1. Okay. So in all, I have n atoms. Okay. And I have how many cells? This is the first cell. This is the second PUC, primitive unit cell. This is the third one. So if you go on, this is the n minus 1 primitive unit cell. Okay. Okay. But there are n atoms because I started counting from 0 up to n minus 1. Okay. Then for mathematical convenience, what Born and von Karman suggested was that this end that is there, okay, okay, the separation between them, let's let it be A. Okay. So the separation here is A. Okay. And instead of going to the next one, which would have been n minus 1, sorry, which would have been n, we stop just before it. Okay. So we stop just before this point. I had to see. So we stop just before it. Okay. And this point, we connect it to this point, to the origin. So when you count, you go from 0, 1, 2, 3 up to n minus 2, then n minus 1, and then the next one would have been n, but it's 0. Okay. So we are saying that atom n is the same thing as atom 0. Okay, atom 0. Okay, so that's what we're saying. Not only that, we are saying that, so after n, the next one is n plus 1. So atom n plus 1 is the same thing as atom 0 plus 1. Okay. And atom n plus 2 is the same thing as atom 0 plus 2. Okay. Yeah, this is 0 plus 2. Okay. So in general, okay, atom n is the same thing as atom n plus sorry. In general, atom n plus little n is the same thing as atom n. Oh, sorry, atom little n. Sorry. Okay. And someone has a question. So this is the periodic boundary condition that we're going to use. Oh, no, we interchanged it. Okay, so if you look up here, oh, sorry. No, sorry. We should interchange it. Thanks. So here we interchange it. We make this N2, N1. Yeah, thank you. So we interchange the states onto N1. And in the next line, we interchange the positions. Okay, thanks. Okay, so this periodic boundary condition that or this boundary condition that we have not used is just for convenience. Okay, so there's no real physics behind it. And in fact, if you are dealing with a nano system, you shouldn't use the periodic boundary condition. We use it because we know that there are a huge number of atoms in the system and a huge number of primitive unit cells. So if you join one end to another, it will make a difference. So this is 0, this is 1, this is 2, and you count, and then the last one is n minus 1. Okay, and then you join it. So you join it here to the next one. If the system is large, this will not make a difference. Okay. So if the number of atoms is huge, then it will not make a difference that you join them. If the number of atoms is not huge, like you have 100 atoms, it makes a difference whether you join them or you don't join them. So when you talk about nanotechnology, which is like a few tens or hundreds of atoms, then you can't use this approximation, or you can't use this boundary condition, because then it will affect the result you get. But in the case where you have n, which is like 10 to the 23, more than the amount of money that anybody has in the world, okay, then we can join the ends and there will be no repercussions, okay? And we do that just for convenience, okay? So what would that lead us to? In this case, it leads to the fact that the wave function at x, okay, will be the same as the wave function at x plus L, okay? In this case, x is NA, okay? So if you look at this, expression that we have here, okay? Big N plus little n is atom n. Big N plus little n is atom n. So in this case, x, I'll write it as NA, and then L, I'll write it as NA. Okay. So this equation is just telling you that psi at NA, okay, is the same thing as psi at NA plus L. Okay. So in this case, our psi is 1 over square root of L into the IKX. Okay. So if you apply this boundary condition, you get that psi at x is 1 over L square root into the IKX. Okay. And then psi plus L is also 1 over square root of L. I use the same relation here. And this will write it as into the IK x plus L. So if you equate both of these together, this will give you that e to the IKX is the same thing as e to the IK x plus L. Okay. So that means that 1 is the same thing as e to the IKL. Okay. Or KL has to be 2 pi times integer. Okay. So K becomes quantized. K cannot just take any value now. is 2 pi over L times integer. Okay, so P is an integer. It can be 0, it can be plus or minus 1, and things like that. Okay. And so if you like, you can write it as 2 pi and integer over NA. Okay. For now, I stick with this. So P is 0, plus or minus 1, plus or minus 2, and on like that. Okay. What does that mean for us? It means if I draw K on an axis, okay, then I can start with this one. I'm sorry. Sorry. Okay. So I can start with this one. I can start here at 0. The next possible value of K is here and here. This is minus 2 pi over L, and this is 2 pi over L. The next possible one will be here, 2 pi times 2 over L. And the next one here is minus 2 pi times 2 over L. And you can keep on going and keep on going here. Okay. What this helps us to see is that, okay. So if I have a region, which I'll call a region, and the length is delta big K, okay? You can count how many K values are there, okay? So the number of K values in delta K is just delta K divided by the distance separation between this and this, which is 2 pi over L. Okay. So that will give me the number of K values that I have in this delta K. Okay. So each of the K value can be occupied by, okay, so by 2 electrons, one spinning up, one spin down. Okay. So when I write psi K, so I can have psi 2 pi over L. Sorry. First, I can have psi 0. So what are the possible cycles you can have? You can have psi 0 and spin up, and then you can have psi 0 and spin down. Okay. In what we are doing, the energy just depend on is free electron. So it just depends on K squared. Okay. So for psi 0 and psi 0, you can try to write the energy. So the energy will just be h bar squared 0 over 2m. Okay, so in this case, it will just be 0. Okay. So the 2 electrons will have 0 energy. Okay. The next one we want to do, the next one, okay. So let's take a case in which you have 9 electrons. And you want to have you want to put the 9 electrons in the system. What should we do? Okay. Because the energy goes with K squared, and you want to put the 9 electrons in ground state. So GS is ground state. Okay, so we want to put the 9 electrons in the ground state. Okay, so because the energy goes at h bar squared K squared over 12, then the first 2 electrons, you put them in psi 0 spin up and psi 0 spin down. The energy will be this h bar squared over 2m, and this K is 0. So the energy will be 0. Okay. Then the next electrons you have, so now you fill 2 electrons. Now you have 7 more. The next one you put in psi 2 pi over L spin up, and psi 2 pi over L spin down. Okay. The energy will be h bar squared 2 pi over L, so K squared over 2m. Okay. So that will be the next energy. So this will be E0, this will be E2 pi over L. Okay. So now you've put 2 electrons there. One is spin up, one is spin down. Then after this, the next one you want to put now, you have 2 more electrons. Sorry, 4. So you have 5 more electrons. Okay. Then the next one you put, you can put C also in psi minus 2 pi over L, spin up, and then psi minus 2 pi over L, spin down. Okay. And the energy is h bar squared over 2m. Okay. Minus 2 power by L squared. Okay. So now you put 2 more electrons in it. So now you have you have 1, 2, 3. So you have 6 electrons you put in. Okay, so we have 3 more electrons to go. Okay. So the next one will be psi 2 pi times 2 over L, spin up. That will take 1 electron, and then psi 2 pi over L, spin down. That will take another electron. So this is, 2 pi times 2. So 2 pi times 2 over L squared. That'll be the energy. Okay. So now for 2 electrons. Okay. Now we are left with 1 electron. Okay. Where do we put this 1 electron? If you want to have the ground state energy, then fortunately in this case we can put it as minus 2 pi over 2 times, minus 2 pi by L times 2. Okay. And then we can put it in spin up, or if you like, you can put it in spin down. Okay. So in this case, the energy will be exactly this h bar squared over 2m, 2 pi minus 2 over L squared. Okay. So we put the last electron there. So the energy of the last electron to put in the system, or in this case, is the energy of the highest occupied. Has a special name. It's the Fermi energy. And some people call it Fermi level. If you go online, some people distinguish between Fermi level and Fermi energy. Okay, but it's just the energy of the highest occupied state. So if you are to draw the energy for this system as a function of K, okay, you have something like this. At this value of K, there are 2 electrons. Okay. The next value of K, let's put it here, is 2 power by L. And here is minus 2 power by L. Okay. So this is the curve for E going as K squared. So okay, so this is the curve. Okay. So the energy is h bar squared, K squared over 2m. So we've put 2 electrons in this state. Now, the next 2 we put in this state, the energy will be here. Okay. So we'll put 2 of them here, and 2 of them here. So we've put 6 electrons in all. Then the next one, we can put it here. Okay. So this is 2 pi over 2, 2 pi over L, okay, times 2. So we put the 2 electrons in this state. Okay, we put 1 spin down, one spin up, 1 spin down. Okay, so this state is occupied, the energy is here. This state is occupied, the energy is here. Oh, sure. I made a mistake. My picture is not great. Let me try to correct it. So this energy should, ouch. This energy should be the same as this energy. So I should put this actually. Sorry. Okay. Okay, so they have the same energy. This one now, we put 2 there. So now we have 8. The last one, okay, we want to have the lowest energy. So the last one we'll put here, and it's just 1. And this is minus 2 pi, 2 over L. Okay. This one here is minus 2 pi over L. Okay. So this is the last one that we put. The energy of this last one, that's is the Fermi energy. Okay, so here the energy is the Fermi energy. So if you have many electrons, then all the higher states will be occupied. And so let's do it. You have more electrons, the states are occupied, the states are occupied. Okay. The K value, you can read it up here. The K value, you can read it up here. The K value, you can read it. The K value, you can read it. So more of them are occupied. Okay. Okay. And let's say this is the Fermi level, depending on the number of electrons you have. So let's say this is the Fermi level. Okay. So this level now. So if you have 9 electrons, okay, this is the Fermi level. Okay. If you have more electrons, the Fermi level shifts. Okay. So let's take a case where I'm going to draw the energy as a function of K. Okay. We can, oh yeah, so the Fermi level changes with the number of electrons you have. Okay. Okay. So in this case, it goes quadratic. Okay. So suppose we know the number of electrons and this is our Fermi level. Okay. That means all the states here are doubly occupied. Okay, they are totally occupied, occupied, occupied. All of them are occupied. Okay, all the states here with all these K values, they're occupied and occupied and occupied. Okay, then this one is empty. Okay, in the ground state, we put all the electrons here. So this one is active. So if you add an electron to this system, you add an electron from outside to the system. The electron you add from outside will stay in this state at the Fermi level. Okay. Another thing is if you add energy to the system, so you heat up the system. If you heat up the system, the electron here near the Fermi level, they will have enough energy, they will move to the energy. Unfortunately, if the energy you give is like this energy, is let's call it delta epsilon, it's too small. Okay. If this electron here, if it accepts the energy, there will be no state for it to go to because all the state it would have gone to, maybe a state here, okay, is already occupied. So it will not take the energy because if it takes it, where can it go? So it can't go anywhere. Okay. The state where it would have gone to is already occupied. So it won't take the energy. So it's only states that are close to the Fermi level. They can take the energy and they can move to higher states that are unoccupied. So in this scenario, all the electrons below the Fermi level, all the states below the Fermi level, they are fully occupied. Okay. So the occupancy is 1. So let's do it. So in this case, all the electrons, yeah, they're fully occupied, so the occupancy is 1. Okay. So I'm drawing 2 plots together. Okay. And then at the Fermi level and beyond, the occupancy is 0. Okay. So this curve that I've drawn, you can think of it as like sideways up. Okay. On the let's do it this way. On this vertical axis, for this one is occupancy. Okay. Actually, let's do it this way. Let's remove this. So this curve I've drawn up to here. Ouch. This curve I've drawn up to here is against K. And now I draw another one. Okay. Where I draw on the vertical axis is the energy. Okay. So it's the energy just like this one. Okay. So it's the energy. Okay. And then on the horizontal axis is the occupancy. Okay. So these are 2 separate plots. One is energy against K. The other one is energy against occupancy. Okay. So actually it's occupancy against energy. So up to the Fermi level, yeah, ouch. Up to the Fermi level, that is here. Okay, the occupancy is 1. Okay, and here, so is 1, and then it drops to 0. Okay, so for those that have energy above the Fermi level, these are the states. They are not occupied, so the occupancy is 0. And up to this Fermi level, from 0 up to the Fermi level, the occupancy is 1. And then beyond the Fermi level, the occupancy is 0. Okay. So this plot now, so you can see all these states are occupied. So the occupancy is 1. So this plot now, I'm going to turn it around. I'm going to flip it, and I'm going to draw it like this. So this is the typical one I drew in class. Okay. But you can see it from this energy against K curve. So this is the typical one we do in class. So this is epsilon F, and this is the energy, and this is the occupancy. And this is 1, and this is 0. So when the energy is less than the Fermi level, the occupancy is 1. And then above the Fermi level, the occupancy is 0. Okay. So this is what you have at 0 temperature. And it's ground state at 0 temperature, 0 Kelvin temperature. Okay. What happens when you start heating up the system? When you start adding heat to the system, the electrons near the Fermi level, they gain energy and they can move to higher states. Okay. So the occupancy for those electrons near the Fermi level will drop. Okay. And then outside, just outside the Fermi level, the occupancy will increase. Okay. So the occupancy will drop. Sorry. Will drop here. And then after the Fermi level, it will increase. This area is exactly the same thing as this area because the occupancy dropped in one case and then it increased outside. So this that I've drawn will be for one temperature. Let's call it T1. The green one is for temperature T equals 0. I'll draw a blue one now for a higher temperature. Okay. Sorry. Okay. So this other one is for temperature T2, which is greater than T1. So more of them will gain energy. Okay. The occupancy will drop, and outside the occupancy will increase. More of them will gain energy. Okay. So the reason why the energy is not evenly distributed is because because of Fermi's exclusion principle. Okay. All the states are occupied like this. 2 electrons cannot occupy the same state. Imagine if Fermi's exclusion principle were not there. Then we can have many of the electrons occupy this state. Many of them will just occupy the state. Okay. And then when you add energy to the system, okay, they can each one can move on to another state. Okay. You can add energy and then they can move here and move here. And everybody has a chance to move out and move out. And even the higher states, many of them can occupy the same higher state. Okay. So here we can have many of them occupy the same state. Many of them occupy the same state as you heat up the system. So this will be for a bosonic system. They don't have anything like 2 of us cannot share the same state. So for fermions, 2 of them cannot share the same state. Oh, sorry. That's why when you give energy to the system, this chap will like to have moved to a higher energy state, but because it's occupied, this higher energy state is occupied, it can't move. So it will not take the energy. Only the people or the level states that are close to the Fermi level, those ones can take the energy and move to the next state. Okay, because there's empty state above them, so they can take the energy and move. Okay. So this is the short thing about occupancy and how energy is distributed. Okay. There was something else I wanted to say, and that has to do with yeah, okay. There was something else I wanted to say, and that has to do with something else. Okay, so this is the short thing about energy distribution for electrons, and it's because of this of quantum mechanics. Okay, you add the indistinguishability of indistinguishable particles. So you add quantum mechanics. That's why we have the wave function. You add the fact that the particles are indistinguishable. Okay. And you add the fact that they're fermions. Okay. These three things lead to the fact that no two electrons can occupy the same state. In the same state. Okay. So all the levels here are occupied. Okay. The ones above are empty. Okay. So if you give energy to the system, okay, electrons that are in a state here will not take the energy to go here. Okay. But the electrons that are near the top, they can take the energy and go here because there's state available for them. So this will happen, but the other one will not happen. Okay. So all the electrons, they don't have the same energy. Okay. So this is a consequence of that. Okay, one other thing that we did in class, which I think is important, is that if you want to know the number of electrons in the system, okay, you can find the number of states that are occupied and multiply by 2. Okay. Number of electrons. Okay. It is 2 times the number of states that are occupied. Energy levels. Let's call them energy levels. Okay. So it's 2 times the number of occupied energy levels. Okay. So if I draw this thing again that I drew before, and this is 0, and then I can take all the k, this k here, this k here, this k here. I take all the k's, and I'll take all the k's. Okay. Okay. I'm going to take from a particular minus k max to a particular k max. Okay. So all these states now, they're occupied. Okay. And then the other states that are not occupied outside. So these ones are not occupied. And all these ones that I drew like this are occupied. Okay. So how many electrons are in the system with occupied energy? So in this case, I'll just do 2k max. I'll divide it by 2 power by L. Okay. So this will give me the number of k states that I have from minus k max to k max to plus k max. Okay. Then I'll multiply it by 2 because each of these states is doubly occupied. Okay. And this will give me the number of electrons in the system. Okay. So I just find from minus k max to k max is 2k max. I divide by 2 power, that gives me the number of states that are there. I multiply by 2 because of spin up, spin down. So this gives me the number of electrons in the system. You will notice that I can write this as 2 integral dk over 2 pi over L. And k goes from minus k max to k max. Another thing you could do is, if you are in 3 dimensions, then everything is like a net. Okay, because in 3 dimensions, you have kx, and then you have ky. Okay, kx will go from 0, and then the next one is 2 pi over L, and then the next one is 2 pi, 2 over L, on like that. Okay, here is also minus 2 pi over L. This is minus 2 pi, 2 over L, and on like that. Along y also, that'll be 0. Here will be 2 pi over L. Here will be 2 pi, that's 2 over L. Below will be minus 2 pi over L. Okay. And then, of course, it's netted. So here will be minus 2 pi times 2 over L. Okay. And on like that. Okay. So if I take a region, I can also ask you how many K points are there. So let's take a region like this. I can ask and say, how many K points are in this region, this blue region? Or if you like, I could have taken a circular region. Okay. And ask how many K points are in this circular region. Okay. So the number of K points there will be this area. Okay. And then I divide by this unit area. So it's 2 pi over L squared. Okay. That's the number of K points that are there. Okay. So if I'm looking for the number of number of electrons in the system, okay, I'll have to find the area up to, let's call it Kf. Okay. So the energy at Kf is the same thing as the Fermi level. Okay. So this is h bar squared, Kf squared over 2m. Okay. So this one is h bar squared Kf squared over 2m and is the Fermi level. Let's do it this way. And this is the Fermi level. Okay. So you can find the area in K space up to Kf. Okay. Area up to okay. Then I'm going to multiply by 2 because each one can have, sorry. Let's do this. Okay. So if I take the area up to Kf and I divide it by 2 pi over L, okay. This gives me all the states, the number of K states that are occupied. Then I multiply it by 2 because each one is occupied by electrons spin up and spin down. This will give me the number of electrons in the system. Okay. So you can also convert this to an integral, and it's 2 integral dkx dky over 2 pi over L squared. And then K, there is 2 integrals, and then the magnitude of K should be less than Kf. So if you like, you can say in this case that the first integral go from Kx equals minus Kf to Kx equals Kf. And then the other integral is, actually I should have done it the other way. Okay, Ky. And the other integral is Kx minus Kf to Kx equals Kf. And then is dkx dky over 2 pi over L squared. And then I multiply it by 2. Okay. And this gives me the total number of electrons that are in the system. And then you can convert this from Cartesian. You can convert it to cylindrical polar. Okay. If you do it in 3 dimensions, Okay, you have something like this also. 2 for the spin up, spin down. There are 3 integrals, and then there's the kx, the ky. And you divide it by 2 pi over L cube. And you restrict yourself to k. The magnitude of k should be less than or kf. Okay. So you have this. You can convert this to, you can convert this on top. You can convert it to spherical coordinates. So because it's 3-dimensional integral, so you can convert it to spherical coordinates. The 2 is still there. Then the integral goes from 0 to 2 pi for phi, and then from 0 to pi for theta, and then from 0 to the same limit like this, kf. Okay. And now I'll use the volume element in spherical coordinate. So that's k squared sine theta, the phi, the k. Actually, let me rewrite it. So it's k squared sine theta. And then is the k, okay. And then is the theta, and then is the phi. Okay. And then everything, as usual, we divide by 2 pi over L cube. Okay. It turns out that this integral you can do easily. The integral with respect to phi, we can do, is going to give us 2 pi. The integral with respect to theta, you can do, is going to give us 2. It will leave only the integral with respect to kf. 0 to kf. And this is k squared, the k. And you still have your 1. This 2 pi by L cube, let's write it as L cube over 8 pi cube. Okay. This integral, can we do it?
Yes, we can.
Okay, what does it give you?
K cube over 3.
Okay, so it's k, yeah, kf cube over 3. Okay. So when you put everything together, this is exactly 8 pi. It kills it 8. It doesn't kill the pi squared. So you have L cube over pi squared. And this is kf cube. Okay. And this is the total number of electrons in the system. Okay. So if I do n over L cube, okay, this is kf cube over 3 pi squared. N over L cube is the number of electrons per unit volume. Okay, so let's write it as n. So if I give you a BCC, for instance, okay, and BCC, let's say is potassium, okay, I give you the lattice constant, then you can easily calculate n, which is the number of electrons divided by a cube. So you have to divide, oh sorry, BCC, there's something at the center. Okay, so you know the number of electrons in BCC you divide, that's the n that you use there. Okay, so now I can write that n is kf cube over 3 pi squared, or if you like, you can write that kf is 3n pi squared to the power 1 over 3. Okay, this is very important. Okay, why? Because then the Fermi level is just h bar squared, kf squared over 2m. Okay, so you can write it as 3n pi squared, h bar squared, 2/3 over 2m. So that's the Fermi level. Okay. This is in the case you have a huge number of electrons in your system. You can calculate the Fermi level this way by knowing the number of electrons per unit volume. Okay. If you have like 20 electrons in an infinite square wave potential, okay, and or even if you have 21 electrons, okay, and you are looking for the Fermi level, okay, the width, let's call the width A. Okay. The energy we already know is n squared, pi squared, h bar squared, sorry, over 2m a squared. This is correct, right? Do you remember from quantum one? So from quantum one, when you do it quantum one, you get your wave function is A sine kx plus B cos kx. Okay. You apply the boundary conditions. Okay. And then that gives you that K has to be n power by A. Okay. And psi has to be A sine n pi x over A. And the energy is just h bar squared k squared over 2m, which should just be h bar squared over 2m. K squared is n pi over A squared. So this is exactly this expression that you have here. Okay. So this is the energy of any level. Now you have 21 electrons in this system. So your Fermi level will be what? Okay. So this is the exercise you need to do. You have 21 electrons in the system. What's your Fermi level? Who wants to try? There's spin in the system, okay? Okay, so who can tell us what the Fermi level will be? Who has an idea?
So can you scroll up a bit? I want to check something.
Okay, what mass?
More.
Okay.
You can come down, sir.
Okay.
21. Okay. Ah. So could that
Yeah.
be h bar squared tau squared over 2m?
R squared, pi squared over 2m. Okay, A squared.
Then, okay, the denominator here is a squared. Okay, yes, yes,
What?
yes.
Yeah.
Okay, so
So what?
dot
Yeah. What will be the Fermi level?
21 squared over a cube.
Why do you want to say it's 21 squared?
Yeah,
You have an idea.
21.
There are 21 electrons, right?
Yes, sir.
Don't forget the
Over
spin. Don't forget the spin. So there'll be two, and then there'll be two, and then there'll be two. So level 1, 2, 3, up to 10, there are 20 electrons.
1.
So this is n equals 1 up to n equals 10. So there are 20 electrons. And then the last one is n equals 11, and there's only one electron. So the Fermi level will be, in this case, pi squared, h bar squared, over 2m a squared. And then your n will be 11 squared. You understand?
Yes, I understand.
Over 2m a squared. Okay. Actually, if you, this is correct, okay. But let's say you have, yeah. So this is the, yeah, so this is the answer you get. Okay. You can try to do the same if you have many electrons. You have many electrons like this. Okay, so you can put all the states here. Okay, so in this case, it's not particularly in a box. Okay, you can think of it as free particles, and in a very big box, the length is L. Okay, so you can also try to do similar things. So there's 0 here, then there's 2 here, then there's 2 here. Sorry, there are 2 here already. And so this is 2, 6. And then this should be 7, 8, 6, 9, 10. Then you can keep counting. I know which state will be the last one. Yeah. So I leave that as an exercise for you to know which state will be the last one. Well, I think there's only one more thing to do. Okay. So this distribution function that we do, okay, which is like this. This is at t equals 0. This is F, Fermi-Dirac distribution. Well, we call this occupancy. This is epsilon. Okay. I'm going to put mu here. One can show that the behavior of mu is 1 over e to the beta, epsilon minus mu, okay, and plus 1. Okay. And you can check that as beta goes to infinity, that is t goes to 0. Okay. Because beta is 1 over kbt. You can check that the curve is exactly this. Okay. Is 1, and then at mu equals epsilon f. Sorry, and then at epsilon equals mu, which is epsilon f. You can check that then it goes to, the occupancy goes to 0. And this is exactly this expression. And then when you, at a finite temperature, this curve, when you draw it, is going to be something that goes like this. Okay. All of them will pass through half. Okay. Because when epsilon is the same thing as half, then it's 1 over, so f, when epsilon is the same thing as mu, sorry, and it depends on temperature also, is 1 over e to the beta, mu minus mu, okay, plus 1, which is 1 over 1 plus 1, which is half. Okay, so at the Fermi level, or at mu, the FFD is exactly half. So it passes through this half. If you if you add more heat to the system, if you go like this, it will still, sorry, it will pass through the half. Sorry. And go like this. Okay, so you have something like this. So the green one is on temperature T1, and then the black one is on temperature T2, which is greater than T1. Okay. And the red one is at T equals 0. Okay. So I think these are the main thing about occupancy. Oh, now, okay. Since the number of electrons does not change, we can write it as the integral from 0, sorry, from 0 to kf. Okay. And then whatever you have there, the k, right? This was what we did. Okay. So it should be the same thing as integral from 0 to kf. Okay. You multiply by the occupancy, sorry, from 0 to infinity. You multiply by the occupancy. Yeah. And then the same thing that you have here, I put here. Okay. Then the k. The only thing that has changed is I added this occupancy. Okay. At 0 temperature, the number of electrons does not change. The number of electrons is still the same, whether you heat up the system or you don't heat up the system. If you heat up the system, you should use a Fermi-Dirac expression because the occupancy near the Fermi level will change. So you need to put this F function there. Okay. You can see that at 0 temperature, it will reduce to something like this: integral from 0 to epsilon f, FFT, okay, plus integral from epsilon f to infinity. So this that I've written, I'll split it this way. Actually, this is true for any temperature. Okay. And then I have FFT, the same thing. The thing that we have here, let's call it W, whatever function it is. Okay, so it's some function which you call W and the K. Okay. So I've split this integral from 0 to infinity to 0 to epsilon f, and from epsilon f to infinity. At 0 temperature, this FFT, well, epsilon f to infinity is exactly 0. Okay. And this FFT from 0 to epsilon f at 0 temperature is exactly 1. So you see this reduces to exactly 0 to infinity epsilon f w dk. Okay. Just like you have here. So you see the expressions are exactly the same. Okay. This is not this is not true for other things. Okay. So you have exactly the same thing. This is not true for something like the energy. Okay. So the energy, you can write it as an integral from 0 to, you have to write it as an integral from 0 to infinity. Okay. And then ft, this w, which, let's not use w, let's use big Q. No, let's use big Q. And then decay. Okay. So this will be the energy at a temperature T. And this Fermi-Dirac distribution will also be at temperature T. Okay. And then you can integrate from K equals 0 to K equals infinity. Okay. So when we're in class, we try to change this to an integral over energy. And that is what's introduced to us the density of state at a particular energy. Yeah. Okay. So I think this is a convenient place to stop. Does anybody have a question? Okay. So um I think we can stop here. If you have questions, then you can let me know. You can send me an email.